Hi everybody, this is Dr. Ricardo. We are going to go over today how to calculate what the edge length is on a unit cell and or the volume of a unit cell given the following two facts. One is I would give you a picture like this picture of diamond here of what the unit cell looks like. So I have to give you the structure of the unit cell. Okay, and we know what the unit cell is. It's the repeatable pattern that the atoms take when they crystallize. So this is the unit cell for diamond. Diamond is one of the strongest substances known to man. It's a covalently bound network solid because there's an array of very strong covalent single bonds that runs through the whole structure. Okay, so if this pattern, if you have one unit cell here, there's an identical one right next to it, kind of like putting tiles on the floor only in 3 dimensions. There's one on the top, there's one over here, there's one on the bottom. This thing would be surrounded, and then there would be millions and millions and billions of these to the point where I could actually see what the diamond looks like to give me the macro structure. So if I give you two facts, and these are the two facts here, the first one is, what does the crystal structure of the diamond look like? What does the unit cell look like? And we are only going to be working in cubic type unit cells, okay? So you don't have to worry about any other shape other than a cube. And the 3 types of cubes that you're responsible for are the simple cube, right? The face-centered cube, which this one is, and the body-centered cube. Okay, so we're going to go over that in a second. So that's the first thing, is I have to give you what the crystal structure is. I have to give you a picture like this. The second thing I have to give you is I have to give you the density, the bulk density of the particular material. And given those two facts, that's all you need. It's really kind of neat to calculate what is the volume of each unit cell. Remember, each unit cell is going to be tiny, right? It's going to be, 5, 6, 7, 10 carbon atoms in size, whatever fits into this box. Okay, so we're going to figure that out in a minute. And once you get that volume, you can calculate what any one of these edge lengths are. They all have to be identical because it's a cube, right? And a cube has all of its edges equal to the same length. So we'll talk about how to do that. So once you get the volume, it's only one more step to get the edge length. Okay, so let's go back a little bit and review. We know every cube in nature, right, has all of its 12 edges are identical, right? So where are the 12 edges? There are 4 in the top. There's 1, 2, 3, 4. 4 in the bottom base. 5, 6, 7, 8. Then there's the last 4 are these ones that connect the top and the bottom. So think about it. Top and a bottom, and then 4 legs. So we're up to 8, 9, 10, 11, 12. So we know every cube has 12 edges. Every cube has 1, 2, 3, 4, 5, 6, 7, 8 corners, okay? And the last thing we know is how many faces does a cube have? Each face, right? A face would be the area up here. That would be one face. So there's that area. There's the bottom face. That's 2. There's the back face. That's 3. There's the front face. That's 4. There's the right-hand face, that's 5, and there's the left-hand face, that's 6. So this is always true for every cube. Okay, in the next slide, we're going to see how the atoms in diamond fit into this unit cell, this repeatable pattern. Okay, it's only one pattern that I can show that if I draw it in a certain way, and I line everything up in a certain way, then that pattern just repeats over and over and over again. Even though some of the atoms actually might not be, you might not see the covalent bond to the other atoms in this cell, which is kind of neat in the case of diamond. But these facts always occur too, right? So these things are memorizable. This stuff is memorizable, and this you can memorize, okay? Every time you're in a corner, just memorize that if you're in a corner, how much of the atom is within this particular unit cell? 1/8 of the atom, and we've talked about that before, right? And if you're in a face, you would be right in here. Think about tennis ball that's embedded right in this face. Half of it would be in this cubic cell, the other half would be in the next one. So anytime you have a face, you multiply by 1/2. So a lot of times you're going to see 6 times 2 equals 3 for the faces. Over here for the corners, you're always going to see 8 times 1/8 equals 1. Okay, that'll never change. Okay, you'll always have that for the corners because you have to have atoms in the corner of any of the cubic cells. Okay, and whenever time you're in an edge would be right smack in the middle of this line, 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 in the middle of this line. Anytime you're living in an edge, actually you don't have to be in the middle, but usually they are. Okay, anytime you're in an edge, you would be 1/4 in this cell, right? Because 1/4 of you would be in here, 1/4 of you would be in the one next to it, 1/4 of you would be on the bottom one, the bottom front one, and one would be right underneath it. So that's why edges are always equal to 1/4 of the unit cell. So what's going to happen with edges is there's 12 of them times 1/4. A lot of times you're going to get 3, right? 12 times 1/4 is equal to 3. And then last, the only other thing you can have besides corners, faces, edges, is you can have atoms or ions that are totally within the interior of the cube. So we have a couple of those. We actually are going to have 4 of those for diamond. If you're inside the cube, you're not shared with anybody else at all, you multiply by 1. So those are our repeating multiples. 1/8, 1/2, 1/4, and 1. Okay, let's take a look at the diamond. So here's my explanation of a diamond. Okay, a diamond, if you look at it, is a face-centered array of carbon atoms. Okay, so again, in this course, we're only going to be responsible for really understanding simple cubes, body-centered cubes, and face-centered cubes. So here's a face-centered cube. So how do I identify it? First, I realize it's a cubic structure. Why? Because I see a cube, I see a carbon atom in every one of the 8 corners. So that's how I know it's cubic arrangement. Second, why is it face-centered? Take a look at this atom down here in the bottom. Half of it is in our unit cell, and the other half is in the cell that goes underneath it. Take a look at this one on the top. It's easy to see. Half of it is in our unit cell, half of it is in the one on the top. How about this one on the right-hand side? Half of it is in our unit cell, half of it is in the other one. How about this guy over here? Half of it is in our unit cell, half of it is in the other one. Okay, last 2. Here's the one in the front face. Half of it is in our unit cell, half of it is in the other. And the last one, this one back here, is in the back face. That's a little hard to see. Sometimes you'll see a drawing where the carbon is rotating around. I'll see if I can get a video of that. And when it rotates around, you'll be able to see that that guy's in the back face. So there's the 6 in the face. Ready? I'm going to go through them again. 1, 2, 3, 4, 5, 6. Okay? So it's a face-centered array. What's in the absolute middle of the unit cell? Nothing. Look, there's nothing in the middle. Okay? But we do have 4 atoms that we didn't talk about yet. We didn't talk about this one, okay, this one, and this one. These 2 up here, and these 2 down here. A little bit hard to see, but they're not in any of the 4 faces over here, or the bottom face or the top face. So we're talking about 1, 2, 3, 4. Those guys are totally within our unit cell. So those are the 4 over here. So to repeat, a diamond is a face-centered array of carbon atoms. Okay, so that covers everything except for those 4 that are totally within it. And here's the extra piece of information with 4 more carbon atoms located within its unit cell. Okay, second piece of information. If the density of bulk diamond is found to be 3.51 grams per centimeter cubed, okay, so that's the density. If you just had a diamond on somebody's ring and you took it off, you should be able to insert it in water and determine its volume and then weigh it to get its mass to find its density. So diamonds should have a density of 3.51. So that's a one quick check if it's really a diamond versus cubic zirconium. The density should be 3.51. Okay, so with everything information on this, what's the question I could ask you on a test? First, what is the number of carbon atoms per unit cell? Second, what is the side length of the unit cell? Okay, now let's go back to our picture again just for a second, because I want you to realize that the side length is not the bond length. The bond length would be this distance between here and here, or this distance here. That's not what we're talking about at all. We're talking about this length here, which is a little hard to see. They're equal, okay? This is a little bit skewed. This length here, any one of those purple edges, any one of those 12 lengths have to be the same, okay? Different than the bond length. Okay, so let me show you the calculation. First, what is the number of carbon atoms per unit cell? Okay, well, we know there are 8 carbon atoms in the corners. Corners are always worth 1/8, so 8 times 1/8 equals 1. Since this is a face-centered cubic arrangement, there are always 6 faces in every cube. Faces are always worth 1/2. So we get 6 times 1/2 equals 3. Okay? And lastly, the 4 interior atoms that are special to the diamond, I don't know another structure that has it that way. Each one of those, since they're interior atoms, are totally within our cube, so I get 4 times 1 equals 4. If I add all these 3 things up, 4 plus 3 plus 1 equals 8. So we have 8 atoms per unit cell. I'm going to abbreviate unit cell UC. So anytime you see UC, I'm talking about a unit cell. Okay, let's take our 8 atoms per unit cell. So 8 atoms divided by each unit cell. That's what's going on in this picture. This picture contains a net amount of 8 carbon atoms, which is pretty dense. Okay, next thing I want to do, I don't want to know the atoms per unit cell. I want to find out what is the mass of each unit cell, because if I have the mass and the density, I can calculate the volume. So the way we're going to do that is 2 steps. The first step is we are going to multiply by the molar mass of each carbon. So I have 8 carbons. Each one has a mass of 12 grams per mole. So let's look what happens to the units here. What happens to the units is it goes from atoms to grams per mole of unit cell. Okay, so the denominator is now going to be moles per unit cell, but we're not going to have atoms anymore because now I've converted to grams. Why? Because we know that the atomic mass of carbon is equal to 12. If each carbon atom has a mass of 12 and I have 8 of them, the total mass of 1 mole of unit cells should be 96 grams. So if I had a 96 gram sample of carbon, I'd have a mole of unit cells. Okay? If I just had a 12 gram sample of carbon, I'd have a mole of carbon atoms, which is not the size of the unit cell. That's not the repeatable pattern to show the crystal structure. So that's always going to be the first step. Take the number of atoms that we got from above and just multiply by the atomic mass of that substance. Now, if the substance, let's say we were doing ice, right? If the substance was a chemical compound, you'd multiply by the molar mass. So if we were doing ice, we'd take the number of water molecules in each unit cell and we'd multiply by 18 because water's atomic mass is 18. So this is either the atomic mass if it's a element or the molecular mass if it's a molecule. Okay, now this is kind of cool. Now we have 96 grams per mole of unit cells, but that's on the macro scale. That's too big. I want to know how many grams each unit cell weighs. So anytime we want to go from the macro scale of moles to the atomic scale of atoms or unit cells, what's our conversion factor? Avogadro's number. Should I multiply by Avogadro's number or divide? Well, listen, moles of unit cells is in the denominator here. So I need to put moles of unit cells in the numerator. And 1 mole of anything, including a unit cell of diamond, is equal to 6.02 times 10 to the 23rd of that substance. That's a mole of anything, right? A mole would be 1 mole of carbon atoms would be 6.02 times 10 to the 23rd carbon atoms. 1 mole of rice would be 6.02 times 10 to the 23rd grains of rice. So in our case, since we're working with the unit of unit cells, 1 mole is equal to 6.02 times 10 to the 23rd unit cells. Okay, look what happens here. Moles of unit cells cancels with moles of unit cells. I'm left with grams per unit cell. 96, 1 doesn't change anything, so 96 times 1 is 1, divided by 6.02 times 10 to the 23rd, I should get a very small answer, okay? That answer is 1.59 times 10 to the minus 22 grams for each unit cell. So this is really cool. Now I know the weight of one of these. This is the mass, better than weight, right? This is the mass of one unit cell. That's pretty cool. So that little tiny number now, I'm going to work with. Ready? I know the mass of one unit cell, okay? And if I know the mass of something and I know the density, I can calculate what its volume is. So take the density formula, which is D is equal to M over V, and rearrange it for V. So V comes up and D goes down when you cross multiply. The volume of something is its mass divided by its density. Now this is really cool. Density is an intensive property. It's independent of the size of the sample. Okay? Diamond has a density of 3.51. Whether you're talking about a giant sample of diamond like somebody's ring, it's 3.51. Talking about one atom of diamond, it's 3.51, or one unit cell like we are. So look what happens. If I take and plug into my formula, I take the mass in grams per unit cell, and I divide it by the density in grams per centimeter cubed. The grams cancel out, right? Unit cells will still be in the denominator, but what happens to this centimeter cube that's in the denominator of the denominator? Well, whenever something's in the denominator of the denominator, it's 1 divided by 1 over that thing. That thing would flip up to the numerator. So check it out yourself, do the algebra. Centimeters cubed is going to be the numerator. Okay? So I wind up with centimeters cubed per unit cell. All right. That's the part of the question. That would be if I asked you, what is the volume of each one of these diamond unit cells? One more step. Last step is pretty easy. Since we have a cube, you can only do this with a cube, right? Any other shape is not going to be so easy because all three sides, the length, the width, and the height, are equal in a cube. So this is a fact for any cube in nature. The volume is equal to the length, each length, width, or height, right? Each one of those cubed, right? Go back to here. Every one of these is identical. This is a length, this is a length, this is a length. So when you have length times width times height, you can take the h and put in an L because the length is the same as the height, and you can take the W and put in an L, so you get length times length times length. Okay, back to here. If that's the case, we have the volume and we want the length, right? So what do? The length then is going to be the cube root of the volume. Okay, if you don't have a cube root button on your calculator, you can put, take this number 4 times 5.3 times 10 to the minus 22nd, put it in parentheses, okay, and raise it to the 1/3 power. The cube root is the 1/3 power, or the 0.333333 power. Okay, but you probably have a cube root button. When you take the cube root of it, what happens to the number? The number goes from being incredibly small, 10 to the minus 23rd, to just regular small, 10 to the minus 8th. This was centimeters cubed per unit cell. So now take the cube root of something that's cubed, it just comes out to centimeters. So the length is 3.56 times 10 to the minus 8th. Okay, so try that on the calculator yourself. Last step. If we want to express this in angstroms, which is a very small unit of length, 1 angstrom is 10 to the minus 10th meters. So this is just converting, but I would accept this on a test. I would accept the centimeter answer. Okay, but this last piece here, 3.56, how do I get that? I take my unit in centimeters, multiplied by, there are 10 to the 10th angstroms in every 1 centimeter. So what happens is, there are 10 to the 8th centimeters in every 1 angstrom. So 10 to the minus 8th times 10 to the 8th gives you, the two exponents cancel, and I get 3.56 angstroms. Okay? But again, on a test, you could just leave this in centimeters. You don't have to go to angstroms. But this is the scale that atoms are attached to. That's what's special about it. It's a special unit called angstroms. It's equal to 10 to the minus 10th meters. Okay? So since we're only converting from centimeters, I only have to multiply by 10 to the 8th, not 10 to the 10th, right? Because there are 100 centimeters in a meter. Try this out yourselves. Make sure you understand it. So this question on a test, guys, can be worded two ways. It can be worded the way that I gave it to you, which is given the structure and density, right? I could ask you, what is the volume of the unit cell and what is the length of each side? Here's the volume, here's the length of each side. Or I can give you the structure and the length of each side and ask you to calculate the density. Okay? So you could do that if you know what substance it is. So the other thing I have to give you is what substance it is. It had to be diamond made out of carbon atoms because you need this atomic mass here. Okay? All right, that's it. Ask me in class if you have any questions about this. That's the end of our special video on calculating the edge length of a cubic system.